There is grandeur in this view of life.
Welcome to Evolution Talk with Rick Coast, an introduction to the oldest story ever told.
In 2005, biologist Michael Skinner witnessed something that shouldn't have happened, at least as far as our understanding of heredity is concerned. It all happened to a few mice. Professor Skinner's mice were exposed to a toxin. Nothing suspicious or new there. That's par for the course in the lives of some laboratory mice. What happened when these mice were exposed to the toxin isn't earth-shattering either. Not that you'd want it to happen to you if you're a male mouse, and especially if you're a male mouse whose parent was exposed to this toxin. In that case, you'd come into this world doomed to life, or doomed to live life, with smaller than average sex organs and a lower than normal sperm count. Now, this wasn't a surprise since the mice could have easily been exposed while in their mother's womb. This could explain the defects. What it couldn't explain was the fact that the next generation also had this defect, and the generation after that. This, as I said at the beginning, shouldn't have happened. It caused Professor Skinner to begin a search for what was to become his white whale.
We started seeing these major diseases occur in approximately 85% of all the animals of every single generation.
Now that's Professor Skinner. Now he wasn't the only one to see something like this either. 7 years later, in 2013, another study saw something similar, this time with behavior. The study was conducted by Brian Diaz and Kerry Resler at Emory University. And during their study, they didn't expose mice to a toxin. Instead, they exposed them to an odor and a few mild foot shocks. If the odor was pleasant, the foot shocks weren't. And the result? You guessed it. The mice produced offspring who were afraid of the smell. The kicker here is, these offspring hadn't even been conceived at the time that the shocks were administered. Yet they were still afraid when encountering the odor.
What we found in the study was that conditioning animals or training them to associate a particular smell with this mild foot shock gives us descendant generations that are slightly more sensitive to this smell, and their brain devotes more real estate to processing the smell.
And that was Dr. Diaz from an interview at the time of the university's press release. This Pavlovian response seems to have been passed down genetically. These results fly in the face of what we previously knew about heredity and natural selection. If I develop over my life an aversion to chocolate, which luckily I haven't, we all know my children won't be born with a dislike for chocolate, or even a love for the music of Nick Drake. Not unless I teach them these things. Our behavior and our biology is a mix of nature and environmental exposures. And what these studies seem to suggest is that the game may be slightly rigged in nature's favor. It's so Lamarckian.
It is not the organs, that is, the character and form of the animal's bodily parts, that have given rise to its habits and particular structures. It is the habits and manner of life and the conditions in which its ancestors lived that have, in the course of time, fashioned its bodily form, its organs and qualities.
Lamarck seems to nail it, and that's troubling. Not troubling that Lamarck was onto something, but because we've spent the last 150 years saying how wrong he was. Now, in all fairness, Lamarck did go a little overboard with his assertion that we experience, or what we experience in life, shapes our bodies. He was all about use and disuse. If you overexerted or overused an organ or body part, and that would be passed on to your offspring. And just like his classic giraffe scenario, their long necks, according to Lamarck, came about because they constantly strained to reach leaves that hadn't yet been eaten. Behavior and habits, he would say, are reflected in the biology of offspring. Without knowledge of the toxin Professor Skinner's mice was exposed to, Lamarck might suggest that these mice didn't use their sex organs enough. Reduced sexual activity, according to him, again, will produce a reduction in sexual organ size. Too much sex and Well, we won't even go there. We now know that natural selection offers the best and the simplest explanation for the shape of the giraffe's neck. It's not the constant stretching and straining to reach higher leaves that caused their long necks. It's because that nature favored giraffes that were born with slightly longer necks, say because of a mutation. And that mutation would be passed on. And because they could consume more leaves, those with smaller necks would be at a disadvantage. Eventually, the population would drift to favor longer-necked giraffes, and so on. But this certainly doesn't help to explain what Professor Skinner saw, and especially what Brian Diaz and Kerry Ressler saw with their mice, and the mice's aversion to a certain odor. Now, if you were born with a mutation, natural selection would predict that if the mutation was advantageous to your survival, which most aren't, then it would be passed on to your children. It doesn't say anything about an alteration to your genes during your lifetime, and especially not alterations due to experience. In the episode on evolutionary psychology, I mentioned the dual inheritance theory, or DIT, which theorizes that our behavior, our fears, and our likes are a mix of nature and nurture. You might be surprised to know that this isn't the first time this has come up either. In the early 1940s, it was brought up by biologist and geneticist Conrad H. Waddington, also known as C.H. Waddington. Now, Waddington was studying fruit flies, and what he was hoping to show was that certain characteristics which are developed during one's life can be passed on or inherited. What Waddington did was he exposed fly embryos to a vapor which caused them to develop a second thorax. At this point, he could say without hesitation that the artificial environment he'd created was responsible for this, a little vapor and a second thorax. He then continued with the environment and selected those flies which developed the second thorax generation after generation. And eventually he began to see flies born with a second thorax that had not been exposed to the vapor. He even came up with a name for it: epigenetics. That's a play on the words epi, meaning outside, and genetics. So an outside factor, in this case the vapor, had an effect on the fly's genes, thus the second thorax. Since Waddington's gift of the term, scientists have debated over its definition. What they all agreed on was that epigenetics exhibits a change in an organism's phenotype. Phenotype being physical traits that are realized because of environmental factors and how it plays upon our genes. It doesn't affect the organism's genotype or DNA sequence.
Every single cell in our body has exactly the same DNA. Yet, when we look at our body, when you look at yourself in the mirror, you see cells that are very different one from each other. So the eye, the skin, the hair, the internal organs, the liver, the spleen, and so on. Each of these organs look very, very different from the other and has a very different function, yet they have exactly the same genetics. They have exactly the same DNA code. That
was Dr. Jean-Pierre Issa, whose work focuses on the epigenetics of cancer in an interview conducted for Cancer Quest. So what we are seeing is the effect an environment has on the activation of certain genes, not the sequence. So if a change occurs due to epigenetic factors, it will still be there when the cell divides. And to be epigenetic, these changes must occur during the organism's lifetime. And that would be true for most epigenetic changes. Most only occur during one's lifetime, and that's it. They don't go anywhere else, nor are they passed on. But if that change occurs during a cell's development, as in Waddington's fly embryos, then it's possible they can be passed on. They may become permanent once natural selection goes to work.
And what we're interested in is how, right now, basic reproductive processing or development occurs in both the testis and ovary, and then how environmental factors affect that. And what that does now, we've found, is induce epigenetic changes, which then can have not only effects on the individual exposed, but essentially get programmed so that all subsequent generations to come will have a shift in either their disease states or phenotypes.
That was Professor Skinner again. You can almost look at epigenetics as being a sort of cellular memory. Once nature begins playing with genetic switches, the status of those switches become part of the organism's developmental blueprint, or part of their phenotype. Another example of this was made famous by a study conducted by geneticist Marcus Pembry. It's called the Överkalix study, after the area of Sweden it focused on, that being Överkalix. It looked at the paternal lines of pre-adolescent men who had been exposed to famine that struck in the 19th century. Pembry's team analyzed historical records, genealogy, and food harvests during the period being studied. Now, what they found was that pre-adolescent men who survived the famine had grandchildren who were less likely to die because of cardiovascular disease. And on the flip side, when there was more than enough food, the grandchildren were more likely to develop diabetes. And that was the paternal lines. The female lines didn't fare so well. If a woman's grandmother was a preteen during the famine, then she was more likely to live a shorter life because of it.
We've got better and better evidence of an exposure in one generation in humans leading to outcomes in the subsequent generations that have not been exposed.
And that was Marcus Pembry himself during an interview with Epigeni. So, as in the Överkalix study, understanding epigenetics helps us to understand what affects our mortality and its origins, like cardiovascular disease and even cancer. The complexities of epigenetics and cancer can be overwhelming, but understanding it can lead to the breakthrough that we've all been hoping for. Instead of cancer being damage to a string of DNA, it can be attributed to those genetic switches I mentioned. Play around with those switches, and you have a cancer cell that's caused by an epigenetic change that occurred during someone's lifetime, like an exposure to radiation or even cigarette smoke. So if it's all due to genetic switches, and the fact that they have been turned either on or off, can we then go in and flick them back? In essence, change the cell's instructions so that when it splits, it's no longer a cancer cell, but a healthy cell. Not only does understanding epigenetic effects help us when it comes to cancer, but also when it comes to something else that we will all inevitably face: aging. We all age, and there's no escaping it, and as we grow older, we show signs of that age. Some of us show the signs of aging more than others. Now, have you ever met a person who looks older than they are? You can blame it on epigenetics. The more times a cell divides, the more chances there are for there to be some sort of damage to that cell, more chances for an epigenetic event. A cellular division happens rapidly when there's damage to tissue, especially inflammation. Stem cells come in to repair the injury. The more they have to divide to do the repair, the more they age and the more we see the results physically. Now, have you ever seen someone who's been exposed to the sun for most of their life? You know, that leathery look that their skin gets? That's the effects of constant tissue damage from the sun and the efforts of their cells to repair that damage. As a result, we see epigenetic damage. It's a fascinating subject and one with all sorts of implications. You know, what it boils down to is the fact that how we look and even how we act can be attributed to genetic switches. Turn a switch off, affect our body type or behavior, and natural selection will provide the filter for which switches persist on to the next generation. Switches can be turned on and off by mutation, the classic Darwinian example, or by the environment, the epi in epigenetics.
Nature does not simply throw away good genes.
And this is theoretical physicist Michio Kaku.
Nature simply turns them off. For example, we have the genes in our own body that would put hair all over our body. And you can actually turn that gene on and create, quote unquote, a werewolf. In fact, in Mexico City, there are 2 young boys with hair all over their bodies that are acrobats in a circus. And scientists have sequenced the genes, and yes, it is a very ancient gene that they have. With chickens, we can actually see the genes for chickens that were turned off because of epigenetics, genes that give webbing between the toes of a chicken, because long time ago, chickens had webbed feet, and also teeth. You can actually bring back teeth inside chickens.
If you think that last part is far-fetched, think again. Just this year, scientists at Harvard University were able to suppress proteins that worked to form the beak of chickens in their embryo state. This was after studying the genes and facial development of reptiles such as alligators. And the result? Tiny teeth, like a velociraptor. And this is only the beginning.
A DNA strand, like me, is a blueprint for building a living thing. And sometimes animals that went extinct millions of years ago, like dinosaurs, left their blueprints behind for us to find.
Evolution Talk is written and produced by myself, Rick Coast. The music on this episode was composed and performed by Waddington Bear. Now, support for Evolution Talk comes from you, simply by listening. Your support is greatly appreciated. And you can always reach me by using the site's contact page or on Twitter, where you can find me at Rick Coast. And most of all, thank you for listening. And until next time, please take care of yourself.
Evolution Talk is a Rick Coast production.